I have a beautiful historic lathe that I love very much. It's capable of accurate work, but it requires some work to make it accurate. And basically, one of the advantages of doing this on a lathe is that it doesn't matter if this isn't concentric to the spindle, because you're only facing off the face of it. So it doesn't actually matter if it's completely central. So it's quite a quick process to set up. The challenge is it's harder to perform running checks because the back of the workpiece is held in a chuck. This is one of the ways that you can make old machines more accurate. This is a tyre gauge tread that will measure in hundredths of a millimetre the depth of tread left on your car tyre. But if you cut the end off and attach a neodymium magnet to the end and some magnets underneath, you can stick it to the ways of your machine, and it will show you where you are in the new lathe. There will always be some tolerance of backlash in the thread. So this actually gives you the correct position of the tool. People were impressed with this, so it went on the Hackaday, picked it up, and I got loads of nasty comments off people. Oh, that's rubbish. and about 10 people went, that's a really good solution and dead cheap, thank you. But it's nice that doing this stuff with PocketQubes, it still allows me to be a maker and to innovate little things that help other guys in sheds and stuff. So yeah, nice. So then I've got my blanks to length. They go onto the milling machine. This is a very atmospheric shot. It's because I have a set of lights around the spindle, and it does a weird thing to my flash. So it looks like I do this in a theatre. So yeah, as you can see, this is then set up on the CNC. So that's my CNC. It's one of them. I've got another one now. This is a pretty cheap machine. It's about as cheap as you can get. It's a CNC 3040, which is a kind of Far Eastern CNC mill router type thing. I read up on these, and the mechanics of the router are really good. They're really robust. The aluminium's good. There's quite a lot of meat in them. The ways are quite straight. But the control systems that they ship with are of variable quality. And when you read up on forums, most of the problems with these smaller machines have come from the control systems that they're using. So what I did was I found a place where I could buy a mechanical kit, and then I made my own kind of controller stuff for it. So one word of warning though, if you are looking at these cheaper CNC machines, is ensure that they have ball screws, reciprocating ball screws as their lead screw mechanism. There are some that are sold that just have threaded bar and a Delrin nut, and you will get no accuracy out of them at all, and they kind of look almost exactly the same. But they're not. They are cheaper, but there's a reason why they're cheaper. So ball screws are very useful. So, as I say, it came and it was just the metal components and none of the electronics. So I've gone for a really cheap, robust controller setup for this CNC. It consists of an Arduino that sits between my laptop and the machine, and it interprets the G-codes that are streamed out of the laptop on the USB. And sends them to the correct stepper motors on the other side. The Arduino is splashed with some open source software called GRBL or Gerbil, and that in turn is connected to the stepper motor drivers. I'm using really cheap stepper motor drivers called TB6560s. Interesting thing about those, there are some versions of them where they have 3 or 4 axes of stepper motor drivers on one board, but they seem to create problems, and they're not necessarily very well put together, and there's some crosstalk issues. So if you do go down this road, you can buy them very cheaply as physically separate boards for each axis and wire them up, and they have been absolutely rock solid. And then I bought a second-hand set actually of NEMA 23 stepper motors that were reasonably powerful, so they would hold position and move a tool quite well. So I would say the whole CNC kit, probably about 500 or 600 UK pounds all in, probably closer to 500, so maybe, what's that, 700 euros, something like that. And it's probably the equivalent of a £1,200 machine by making this side myself. So the process of the CNC machining, I'm sure you're quite reasonably familiar with this. There's CAD, where you draw the shapes, and you can use there's some free tools like Inkscape, which I'm a great fan of, and then there's things like Fusion 360 that we can use. I would say 2D is fine for pocket cubes if you're designing a sort of tube-based chassis for your pocket cube. And in fact, there's some advantages over designing it in 3D. Part of that is when it actually comes to machining the pieces, you might not actually consider it a 3D piece in the sense of a 3D model, because you might have to adjust the orientation of it because that's the only way you can clamp it to the machine or something. So actually treating each face separately as a 2D structure often works better in machining terms than 3D. And then there's the CAM process, which is where you convert your drawings into tool paths. So you set up the types of cut, the type of tool, where the feeds and the speeds and the rates that it performs these operations. And the challenge with CAM at a kind of amateur level is the software is either, it's like that sort of pick two things. It's either cheaper or even free, but much more complex to use, or it's really, really intuitive and simple to use, but very expensive. So my examples of that are Inkscape will generate G-codes, and you can use it to create good tool paths, and it's really, really good, but it's really convoluted, and it takes quite a lot of learning. In the middle, there's things like Fusion 360 has fantastic tool path creation within it. It's an absolutely amazing product on lots of levels. It's quite complex to learn as a sort of CAD package. It's not too expensive as a, not as a student or a business, as just an individual, but it is cloud-based, which puts some people off, and also it's Windows only, which puts off geeks like me who want to do everything in Linux. And then there's a British company called Vectric who make Aspire, and that's a great product. It's super intuitive to use. A friend of mine has a license for it, and it's just brilliant, but it costs a fortune. I mentioned this 2D versus 3D thing. This is my cheap 3D printer. And for me and Stuart, working on OzCube 1's chassis, in, as I say, completely different time zones. So one of us is always asleep or drunk. That's kind of our working arrangement. Actually, 3D printing has been really, really useful because he can bung me an STL file. I get up on a Saturday morning and look at my emails, and there's a new STL file, a new revision. I chuck it on the 3D printer, and then a couple of hours later, I can be looking at Stuart's latest crazy challenge he's set me from the other side of the world. And that's a really, really fantastically useful way to collaborate. A slight challenge with it is, though, is that additive stuff does stuff that's very difficult in machining. So my one sort of, if there's one word of wisdom amongst all this stuff I'm talking about, it's if you are on a team that's building a PocketQube, I would suggest having somebody who's got some machining and like sort of mechanical experience on there is really useful. Because, for example, Stuart once came up with a bracket scheme that just kind of wasn't possible. It was like, it could only really be 3D printed, it couldn't actually be machined out of a product. And so yeah, having somebody who, and also not just designing all your stuff in 3D models can be quite useful. Oh, that's gone the wrong way. Another issue that crops up sometimes is bracket making. Oh, so bracket making is complex. In fact, I'm going to go back to that slide. Bracket making is complex because, well, it's very, very small. They're very, very fiddly. And really, what needs to happen is that every mating surface of the bracket needs to be machined, so it's got a really nice kind of surface finish. And also the inside of the tube where the bracket connects needs to be spot-faced. It needs to be machined as well. And because otherwise, if you put two pieces of stock together with unmachined edges, you will get a skew. It won't sit. I'm exaggerating, of course, but it won't sit completely flush, which obviously reduces the mechanical strength of the joint, but also throws out, by the time, if that has a standoff into a threaded bar, by the time it's got 50 millimeters away, you could be a good few degrees off axis. So brackets are, and also brackets are really hard when they're sort of 6 millimeters cube to kind of hold in machining terms. They're really difficult to kind of hold and work on. So my last little thing is I've come up with what I quite like as a little concept for a PocketQube design, which is basically a bracketless system. So this chassis could be skeletonized in any way and could have any kind of holes in it. And it's finished on either side with two end plates currently just made out of pieces of FR4. But inside, and these FR4 plates sit flush in a rebate milled into the external edge of the PocketQube chassis. And then inside, I have a stack. This happens to be PQ60, but it could be, a different spacing would be fine. So this is my stack coming this way, and then the machined faces of these standoffs receive the top plate, and I can tie it all together. The advantage of this is that they don't connect to the sides, so all those kind of tolerance and fit things are not an issue. And also, it's kind of much more easier to realise when you're a hobbyist with a family and a job and an unrelated career and stuff. It'd be a quicker thing for me to make for somebody. And also, it leaves all of the surface of this to be skeletonized. So at any point, you could attach a fixing. So Stuart was saying about the challenges of finding places to put his tapped holes for his PV arrays, and routing for cables and stuff like that. You can use any of the surface of the outside pretty much, can be taken away and subtracted from the chassis form. So I think it's quite a nice solution. So that's just a picture of the chassis and the internal stack with just some PQ60 blanks that I turned up. And again, this is all really useful stuff for the CNC machine, making little FR4 base plates and PCB milling. You get a lot out of that. So that's essentially it. Apart from this is one of my proudest achievements. So it's interesting that even like this is a small piece for Unicorn 1 that I've made for Tom, and it's quite interesting that even in sort of industry, it's quite hard in the UK certainly to find machine shops that will do these one-off small pieces. So actually, it's interesting that look into your kind of model engineering communities. Might be a good way that you can kind of meet makers who can work to really high tolerances and produce really good quality components at either for free because they're passionate like I am, or a vastly reduced cost. Because a lot of these companies just wouldn't take on making one or two tiny little pieces. So that's it. I'm here all day. I'm giving these models to Rakesh to take back to Nepal to play with, and I hope you've enjoyed that. And thanks for listening.
Thank you, Joe, for this very entertaining and useful talk. Is there any question for Joe?
Yes, I have two actually. Have you considered doing 3D printing of aluminium to do the chassis themselves?
Yes, it could be done. It's quite expensive. Yeah. Certainly if you want to do lots of iterations for amateurs, the cost would be prohibitive really. For people like myself and Stuart who are doing it as a hobby essentially, it would be prohibitive. But yeah, it's a great solution. So I made some components for Paul Casilla for some of his thrust experiments, and we 3D printed some really accurate waveguides in silver and stuff like that. It's a fantastic way to do it, but yeah, expensive at our level.
Mm-hmm. And the second question, back to the pictures where you showed with the bracketless.
Yeah, do you want me to go back?
Yeah, if you could.
Cool.
Because there was something I'm not sure if I saw well or not.
Sorry, I'm going to have to go through them again. Tapping out some slow morphs if anybody knows it.
The next one. Next one? Yeah, those small cubes.
Yes.
Are those just being used to hold the whole stack in place, or are they also connected to that base plate over there and to the rest of the chassis?
They're just standoffs. So
it's in the next picture.
Yeah. So
okay.
This bottom plate here is one of these, and then these are the connectors for this plate on the top.
What I was gonna get to next is, have you taken into consideration vibrations during launch and how that whole thing, especially because it's not bolted to the sides as well, how it might vibrate within.
But if you think about it, it's mechanically the same. In fact, it's mechanically stronger than those pocket cubes that are flown where they've just done a threaded bar from the base
yes.
up through a stack. And also you have, because the two end plates will have a torsion this way,
All right.
so that will take it out. And also these are a press fit.
Okay.
So there's an interference fit between the edge of the aluminium and the piece, and also the torsion of the stack pulling itself together this way. So I haven't done any testing of that, but my gut feeling would be it would be stronger than, say, you know, a direct off a base plate type design mechanically.
Thank you.
Good question.
Right, thank you. I just wanted the main structure. You've got lots of the chassis. You've obviously got lots of thin sections. Have you considered a sheet metal approach?
Yeah, it's again, it's it's about being an amateur, really. So yeah, if I had a really nice high-end kind of brake system and I could do accurate, repeatable kind of sheet metal stuff. I mean, one of the advantages of the tube-based chassis is that because the main bulk of these faces is formed, it takes out a lot of the tolerances. So, you know, it would only take, if you're, you know, fabricating a side and then putting another piece on top and bolting through, it would only take a very small tolerance on one of the pieces to throw all the structure beyond the diagonal tolerances of you know, a PocketQube launch provider would want you to have. So that's kind of why, for simplicity's sake, we've looked at these tube-based things. But it is if you've got lots more money and you've got an access to you know, a big engineering shop, that's a little route to take, definitely. Oh.
Yeah, the last one, because we're running a little bit late. Yes.
How do you machine the interference fit on the internal side of the square section? Because I can't see how you can fit a mill inside.
For this one?
Yes.
Yeah, so, well, you can fit a mill in if this piece is held vertically, and then I use the radius of the tool sets the radius of the diameter of the board that goes into it. So basically the tool is zeroed in a corner and would do cuts like this. And it's actually quite nice because, without getting too technical, you can use a slot cutter instead of an end mill because it's open on one side. You can ramp into the cut, so you can get a reasonably accurate cut. Not so much on these quick models, so don't look at these ones too closely, but you can. Yeah. Thank you.
Okay, thank you, Joe, again. So we move on to the next one, and the next presentation will be given by George Addison from Catapult Space Application from UK.